Thank you so much. Thank you very much. Thanks for the invitation. I really appreciate this chance to speak and also appreciate everything you've been doing all this time to keep the community healthy and vibrant. I'd like to talk to you today about something that we're thinking of as sort of a version of Murphy's Law for gerbes. So let me first tell you what I think is in some way the main result, although I won't actually really explain the main result. I'll talk around it. Please tell me anytime if there's something that is unclear. Feel free to interrupt me. If you can't see something broke, please just yell at me. This is joint work with Dan Bragg, my former student. He's great. He's going to be applying for a job soon. He's an amazing mathematician. Here's one version of the thing that we proved. Let's say let M be the stack of smooth projective curves. And don't worry, I'll put this in context in a second, but let me just say this, okay? Let K be a field and curly G to spec of K, a gerbe with finite inertia. Then there is a K point. And let me say it like this, all right? A K point over K, all right? Such that the residual gerbe of P is G. All right, is up to isomorphism. All right, I will explain what a gerbe is, and I'll put this in context for a while now. But I want to say, what this is telling us is all the zero-dimensional structure that can occur in the stack of all curves is sort of arbitrarily bad. So let me sort of say really why I think of this as sort of a Murphy's Law. And this is maybe like the first iteration of what we might mean by something like this. But you may recall a paper by Ravi Vakil from, I don't know, 20 years ago that was related to some ideas that Joe Harris had, where he showed that roughly speaking, any deformation type of finite type over Z occurs locally in many moduli spaces. and the way that he did this was he first started with these results of Myav that are basically a modern version of classical projective geometry, like Desargues' theorem and the whole business about division rings and so on and so forth. And then leverage this to get any kind of singularity type. Maybe I should say any singularity type. Maybe this is a better way to say it. Any singularity you can define over Z occurs on the moduli space of surfaces of general type, things like that. All right, so he called this Murphy's Law because the idea was no matter how nasty the behavior is that you are sort of predicting, you can find it somewhere in a natural moduli problem. And the reason I'm thinking of this as sort of analogous is this result that I'm describing, talking around. This, in a way that I'll explain, it kind of says that any obstruction to the existence of a K structure on a curve over K bar is realized. That's one way to think about this, all right? So if there's some point in this stack of all curves that realizes that has this particular type of obstruction, and I'll explain the obstruction in a second, it goes back to some very classical ideas. And of course, the interesting question, I think maybe that we haven't addressed yet, we didn't start thinking about this yet, maybe you will, is whether these two things can happen at once. So that is to say, one might wonder does any DM stack, let's say, of finite type over Z occur locally in the stack of varieties? This would be kind of a merging of the two things. So Bakil talked about, the deformation space of a point, the singularity type. We're talking about obstruction problems over a point. And you could ask if you could put those together and you sort of get any kind of local deformation obstruction problem to occur in the stack of varieties. I don't know the answer to that. It seems likely though, doesn't it? Okay, before I explain, more what I mean by the context here, I'm wondering what questions may have already come up for you, or concerns or something like that. My face goes this way because I put all of your faces over there. So I'm sorry, I'm looking at you, not at the wall. I see somebody talking, but I don't know if you're asking a question or if you're just talking. Maybe you're just talking to somebody. Okay. Right. So let me talk about some sort of historical threads that I'm pulling, that we sort of pulled as we were thinking about this. Okay. The first one is this interesting kind of old style question about the field of moduli versus the field of definition. So let me say first how this was stated classically, and then think about it in a more modern way and do some examples. So the classical phrasing of this goes like this, and it looks kind of weird to modern eyes. Let K be a field, and C over K bar a curve or a variety or whatever. Doesn't matter that it's a curve. This is totally unimportant. All right. And I mean a proper smooth curve. Choose your favorite genus, make it big. I don't know. All right. And now you could think about where you can define C. So one way you could imagine is if you have an equation for C, the coefficients generate some kind of a field, and certainly C can be defined over that field. But you could also think about one consequence of that, which goes like this. You could consider the sigma in the Galois group of, say, K bar over K, and let's say K is perfect, or let's not worry about inseparability issues. Those are really unimportant, such that when I base change C by that automorphism, so that is when I apply the automorphism to all the coefficients, the curve I get is isomorphic to C. Okay, I'm not saying it's the same equation anymore. I'm saying that the curves are abstractly isomorphic. So we get a subgroup H in the Galois group of K bar over K. And the fixed field for this group, K bar over H, this is the field of moduli. Let's see, field of moduli. It's just one of these things. I think it's also, in an algebraic closure, it's the intersection of all the fields of definition. There's various ways to say what this thing is, but it kind of seems like, a natural, a kind of field that just naturally comes up, right? And it's related to this question of whether the curve is defined over the field that we're talking about here. Let me see what the modern phrasing is of this. In this, at least in this context of curves, this curve C corresponds to a point, so to speak, in M. Remember, this curly M is the stack of, this is the stack of curves. Okay. And let's just assume the genus is at least 2. And I mean, I don't want the funny business is not important. All right. So let's say genus is at least 2 for now. And now there's a coarse space. Let's call it pi from curly M to Roman M. And what is the field of moduli? It's the field of the point in the moduli space. So is the residue field of pi of P. So that could be some tiny field. It could be some big field. This could be a geometric generic point, I mean, whatever. There's all sorts of things you could start with here, but you get a well-defined point in the coarse space, and you can take its residue field. And that's the field of moduli. So the basic question that people thought about when they noticed these things is C defined over its field of moduli? So far, so good. It's a thing you can do. It's a question you can ask. So let's just talk about a couple examples, because I think this is illuminating in various ways. Let's see here. So these are all non-examples, even though some of them are usually thought of as examples. But we'll come back to that maybe. Okay, let's take the genus of C to be 0. I know this is not concordant with what I wrote here, but this is just for this modern phrasing of it. Of course, the original phrasing has nothing to do with whether the genus is large. Okay, well, what's the field of moduli of a genus 0 curve? Geometrically, there's only one example. So the field of moduli is K. Field of moduli is K. Because there's only one. I mean, of course, the base change is isomorphic to C because it's another curve of genus 0. Geometrically, it's just one of those things, right? Okay, but the curve doesn't have to be defined over K. Okay, but let's see. How am I saying? Now that I'm writing this down. But for example, non-split conics. Oh, this is terrible. What I just wrote. Oh. The way I defined this, actually, it is unique. Oh, and P1 works. Sorry, I got ahead of myself there. This is a little dangerous the way I've set this up. Okay. Because I did something a little bit stupid here, which is no, this is fine. It doesn't matter. Okay, so far so good. So geometrically you get P1, everything's cool. Now let's think about the genus of C equal to 1. All right. So now the Jacobian of C is an elliptic curve. And we know from explicit calculations, we know that we can make a curve with a given J invariant. Okay, over K. Right, so the J invariant, this gives the field of moduli. And we also know that we can explicitly with equations make an elliptic curve with that J invariant over K. So the Jacobian is certainly going to be defined over K. And now, again, the way I phrase this, since I'm thinking about curves over K bar to start with, they're isomorphic to the Jacobians, and so that curve will be defined over K, over its field of moduli. Okay, is this making any sense? Tell me if I'm getting confusing. Okay. Now let's think about genus 2. So I guess maybe it's worth, I don't know how to say this. Like the important point here is that this is just like an explicit calculation that you just do. And this is just, sort of the classification of genus 0 curves. Okay, so those are sort of ad hoc. Now, when the genus of C is 2, there are explicit examples, I think written down by Shimura, of a C over the complex numbers with field of moduli R, but that don't descend. I mean, there's actually like explicit equations. We have one written down in the paper. We haven't posted our paper yet. I don't know exactly when we're going to do that, but you can find those examples written down in all sorts of places. All right. So there are these explicit examples, but you might wonder like what's really going on. I think the genus 2 case is the first case where you start to see what's really going on, and it has to do with the fact that 6 is 2 times 3 and 4 is 2 times 2. Okay. So let me tell you kind of a reason how you can start to see the genus 2 picture getting a little interesting. So let's think about sort of an abstract reason that such a thing would be true. All right. So if you think about the canonical linear system of a genus 2 curve, what do we get? We get C to P1, and this is branched over 6 points. Now, of course, it's not P1, right? P1 has coordinates. That's what P1 is. The canonical linear system doesn't have coordinates. So you don't actually get C mapping to P1. You get C mapping to a genus 0 curve with a branch locus of order 6. Okay. And so, I don't know, let's say we've got C over K bar. Let's put the K bars everywhere. And so here delta is 6, right? So now here's a trick. Why can you make this a 2-to-1 cover? You can only make a double cover branched over a divisor if that divisor is a multiple of 2 in the Picard group. So if we want to make something with small field of moduli but not small field of definition, then all we have to do is make a divisor of degree 6 that's not a multiple of 2 in the Picard group. Right? So if we start with a pair, D delta with, let's say D is a non-split conic, and delta in D, a divisor of degree 6, then we can consider this sort of weird looking moduli problem. A moduli space like this. I'm just going to write it sort of set theoretically. Let's call it maybe curly n. It's the C mapping to D such that, well, let's see here. C is a double cover branched over delta. This makes sense. I'm considering just the double covers branched over delta, double covers of D. Now you can't have this. So notice, so maybe one thing that I didn't explain clearly here. Delta is not in 2 times pic of D when D is a non-split conic. Because it's 3 times an anti-canonical divisor, but the canonical class is a generator for a non-split conic instead of O of 1. And so this moduli space has a point over L if and only if delta L is in 2 times the Picard group of DL. Okay, and this is a non-trivial condition. All right, does this make sense? So over any extension, I have this curve. The field of moduli is still very small because the moduli space is defined over K. So sort of the moduli space N, it has underneath it this field of moduli, and that's K. But the field of definition of these curves, they're only defined over points of N itself, and those are only possible when delta becomes a square in the Picard group, becomes a multiple of 2 in the Picard group. All right. So I just want to zero in on what are the structure of N that sort of matters here. Well, N has 1 geometric point up to isomorphism. There's only 1 such double cover, geometrically. If you think about it, you can see that. And also any point of N has automorphism group Z mod 2. That is to say, the hyperelliptic involution and this is an example of a gerbe. Okay, I will now say a little bit more what a gerbe is for the benefit of people in the audience who aren't familiar with them. But maybe I'll pause here and ask what questions, concerns, confusion you might be experiencing right now. Hearing none, and assuming that either everyone understands or is currently looking at Facebook, which is also fine. I will continue. So let me sort of state slightly more formally what a gerbe is. Right? So a gerbe over S could be, S is whatever you want it to be, but maybe it could be a scheme or a field or whatever, right? A site is a stack curly G to S such that one, G has objects locally over S, and two, any two objects are locally isomorphic. So we're just trying to capture this notion of what we just experienced with this double cover, where you've got one geometric thing, really, but it's descending in all these different ways, and the descended versions are not isomorphic over the small things, but become isomorphic over bigger fields. So, for instance, one way to get such a thing, I mean, at least approximately speaking, given a stack such as M, which could just be M, and a point and a map from, say, spec of K to M, we get a gerbe on spec of K, or maybe on well, I'll say spec of K, but this is not a super good, this gerbe is going to be trivial. Maybe I should say, well, let's just leave it as K right now. CP, which is the object's locally isomorphic to P, and if you're more careful, really you should do this. You really should sort of make it over a smaller field, over the, so to speak, residue field of P instead of just over K, where you're just making a trivial gerbe. All right. So this gives you, if you do it this way, the sort of more subtle. Oops, I just changed the color. The more subtle version of this is called the residual gerbe. So there's a residue field for a point on a scheme. There's a residual gerbe for a point of a stack. All right. And the standard example, again, with our stack, you know, M, the stack of curves, we've got M mapping down to Roman M by this coarse moduli space pi. And if I have a P mapping spec of K to curly M, then the residual gerbe is I take pi composed of P, I take its image, I take pi inverse of it, and I take the reduced structure. So this is a reduced structure on the pre-image of the image in Roman M. Okay. So you see that this is, we talked before about how the field of moduli is the residue field of that image in Roman M. And here we're saying there's actually a little clump of moduli over it, and that is holding all the information about fields of definition. That's the residual gerbe. Okay.
Okay, so I have a question.
Please.
Could you explain why you take this red thing? I mean,
the reduced structure?
Yes.
Yeah, because if you think about, so I guess the one example would be if you say act by a cyclic group on a line, and you take the quotient. So if you think about, you know, like mu n acting on A1 just by scaling, and you think about taking the quotient and you want to isolate what's happening at 0. So 0 should have like a b mu n. It should have, it's 0 with a trivial action of a mu n on it. But if you think about what is the quotient, what is the coarse moduli space? This is x goes to x to the n. Those are the invariant functions under the scaling by mu n map. And if I just take the pre-image of 0, I actually get a thickening of 0. I get k bracket t mod t to the n with the scaling action on it. But that's not, the residual gerbe should just be the structure sitting at 0 itself. So I have to take the reduced structure on that stack to get what I want. And this is generally how it always, this is always, the local structure of GM stacks tells you that sort of this, it's always going to be kind of look like this.
Okay, thank you.
Right. Okay. So that's what a gerbe is. You can, I sort of explained that the gerbes carry the obstruction data about fields of definition versus fields of moduli. Now, let's see, I want to explain for a moment one other aspect of this picture that's important. All right. So let me remind you for a second about a natural sheaf of groups that's sitting on top of any stack. All right. So any stack X comes with a canonical sheaf of groups called the inertia stack. And it's just a sheaf of automorphism groups. I'll write that down. Inertia stack, what is it? Its value on a point P is the automorphisms of P. Okay, so if you think about, if you experience these things enough, you realize that the automorphisms of objects together form a sheaf on the stack, and that's the thing that we call the inertia stack. And there's some formula you can write down in terms of the diagonal and fiber products and blah, 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 blah. But it's just saying that the automorphisms glue together to give you the sheaf of groups on the stack. And one thing you should know is that this thing acts universally on all the relative geometry over the stack. So every sheaf F on X admits a natural right action by I. And the reason I'm saying this is that I'll come when I loop back around in a little bit to thinking about how to make obstruction problems exist in M. You'll see that it has to do with kind of rephrasing equivariant geometry in terms of the relative geometry over these gerbes. And the equivariance is built into a gerbe because of the inertia action. This is what I'm trying to kind of convey. So let me give an example, because this example is simultaneously unbelievably confusing and also slightly illuminating. So let's say that BG is the stack of right G torsors. All right. And so we could ask ourselves, what is I? What is the inertia stack? Right. So so here's the thing that makes this, here's the thing to be very careful of. This is not constant. I is not constant. I is not constant. Okay. So like the automorphism group of the trivial torsor is G. Okay. But in general, the automorphisms of some torsor T, this is an inner form of G, as you all know. And so that's telling you that the inertia stack is not actually constant. Okay. Now here's where it gets really weird. All right. So a sheaf on BG, this is what we all learned as children. I mean, let's think about like a, I don't know, a coherent sheaf or something. This is a G equivariant sheaf on a point. If you're working with sheaves on the big side or something, it's just a sheaf on the big side that's G equivariant, but let's not. Right. So you learn about like coherent sheaves on BG are the same as representations of G, right? This is the thing everyone learns when they first learn about BG and stuff like this. All right. And now I want to just point out that that is a description of a sheaf on BG in terms of the sort of simplicial thing you get from a cover, where the cover is a single point. And so that's how you might think about the equivariance. But I just want to briefly connect that to the canonical right action of the inertia here, because it's actually built into the sheaf in a sort of natural way. It doesn't really have to do with the presentation. So let's see here. So for example, I itself, I, the inertia stack, what is this? This is supposed to be some G equivariant sheaf on a point. This is G with G acting on itself with a conjugation action. Okay. So for instance, if G is abelian and G acts trivially on itself, that does say that in that one case, the inertia is actually a constant sheaf. All right. And now, if you think about what is the normal, you've got this this right action that I told you for the inertia is supposed to act on the right. Now I'm telling you, in terms of this model where we think about a sheaf as an equivariant, G-equivariant thing, and the equivariant model of the inertia is G itself acting by conjugation, what is this right action? Well, it sends F comma gamma to gamma inverse F. Okay, so the inertia action is up to inversion equivalent to the G equivariant structure on a sheaf. That's what I'm trying to say to you. And as a fun exercise, if you feel like doing an exercise, you should check that this map is itself G equivariant for the inertia actions. Okay, and that is a little bit confusing. Right. Oh no, wait, sorry. Let me say that again. You should, if you think about this as, if you think about sheaves on BG as equivariant sheaves on a point, and I'm telling you here, this is the inertia action. You should check that this is equivariant for the actions I just described, G acting by conjugation and G acting on F by the action. This is also an equivariant map. So the sort of equivalent between equivariant things and geometry over BG, it really doesn't make sense. It's worth checking that this is actually equivariant in the equivariant formulation of everything. Is that all right? Okay. So let me remind you of one other little thing here that Giraud taught us. Giraud and Grothendieck. And let's just think about the case where the inertia, let's say the inertia is abelian. There's of course you don't need it to be abelian, but they need this idea of what's called a band, and I don't want to deal with it. All right. So if the inertia is abelian, or maybe we should say G is abelian, then if I take a gerbe X together with an isomorphism between G base change to X and the inertia, so in this abelian case, this is the same thing as H2 of spec KG. Okay, so there's a non-abelian version of this where you need to use bands. Right. So what am I trying to say here? What am I doing? We've got these gerbes that we've just saw naturally arose from genus 2 curves, these special moduli problems that are sort of concentrated at a point. They naturally come with a sheaf of groups that naturally acts on everything. If you unwind it, the action is just what you're used to anyway. So that's the, when you're used to thinking about BG as just the stack of, as carrying equivariant geometry. And these objects, at least when things are in our comfort zone, they're parameterized by our usual chromology group. There's a chromology group that is capturing all the data about these tiny little moduli spaces. And in general, this is sort of how you define this thing when G is non-abelian in terms of gerbes. You have to be a little bit more careful than what I just said. So before we were asking this question, is a curve defined over its field of moduli, right? That was this classical question. The refined question that you sort of are led to when you start to notice how these things break down, maybe, I mean, this one looks a little bit like a fishing expedition, but we could say given C over K bar, so given one of these curves, it's going to have some field of moduli, right? What is its gerbe of definition? Now, of course, the field of definition is not unique. We know that. I mean, it's already defined where you've written it down over K bar. It could be defined over a smaller field this way. It could be defined over a smaller field that way, and so on and so on and so on. There's actually a whole moduli space of definitions. It's a gerbe. It's the gerbe of definitions. So what is the gerbe of definitions? What is the gerbe of definition of C over its field of moduli? Right. So in the example that we had before, where we had some divisor inside of a non-split conic D, then here the automorphism groups for Z mod 2, it's abelian, so we can think about this gerbe as a cohomology class, and the class of this non-split conic in H2 of spec K mu 2, also known as the two torsion and the Brauer group of K is the gerbe of definition. Via Giraud. Okay, so there's an example. So the one kind of mechanism we had, for making these things, we sort of see what it should be. It should be this. The non-split conic corresponds to this Brauer class, and that is capturing the gerbe. That's not very surprising, is it? Okay, so now a general question you could ask yourself. Oops. Is what gerbes of definition exist in M? This is slightly different than what I said, and my answer is slightly wrong relative to how you might interpret this question, but I'm going to say it anyway because I think it's also probably true based on what we've understood so far. The answer is all of them. Okay, and now the reason the fudge here is coming from this question of, do you consider M or do you consider M base change to K? So if you take M base change to K, you can get any gerbe over K. M itself, of course, you're not going to get, the residue fields are not, they're not all fields. So you have to be careful how you ask this question. If you mean it for just the residue fields of M, or you're allowed to base change to a field K and then look for a gerbe there. Okay, this one we definitely can do. I think we're pretty sure we know what's happening there too. Okay, so that's what I'm trying to tell you about. That's what I'm trying to say. What comments, questions, thoughts, or feelings do you have about the field of moduli, the gerbe of definition, that kind of stuff? Okay. So there's another historical thread now I want to pull here. And that's this idea of a versal torsor. And these are just amazing. If you've never seen these before, I don't know how many of you, maybe all of you have. I don't know. I don't know all of your backgrounds. This is one of the most amazing things in mathematics, in my opinion. All right. So let's say that G is a linear algebraic group. And let's just choose an embedding into a faithful representation. Okay. And now there's this amazing thing that happens. So consider X to be this quotient of GLN mod G, which looks very pedestrian. And it's equipped with the morphism, the projection map. So we have GLN mapping to X, and I'm going to just call this T so it looks, it looks fancier, I guess. And what is this? This is a left G torsor. Now there's a miracle. Let me tell you what there's a miracle. Let me maybe state the miracle first. For any field K and G torsor S over spec of K, there exists a map P from spec of K to X such that S is isomorphic to, P inverse of T. So I've got T mapping down to X. I've got spec of K here. I've got S here, and this is a Cartesian diagram. Okay. Every torsor over a field is pulled back from this one G torsor that just comes from this single faithful representation from this embedding. How amazing is that? I think it's super amazing. And the idea, basically this is Hilbert's theorem 90. Well, let's see here. If we take the G torsor and we extend scalars to, GLN cross S modulo G. So this goes to a GLN torsor. Well, we know GLN torsors over fields are very well behaved. So we know with a diagram like this, let's see here. And here's the key. I have a section here. This is Hilbert. And then I can chase the point down here. So this gives me a map. Maybe I should make this green. This is terrible. I'm very bad at this. I'm sorry. And then if I pull back, you know, if I think about what's happening in this diagram here, if I pull back a point, okay, I'm gonna get S. All right. So Hilbert's theorem 90 and this representation guarantees that you've got this thing that carries all the torsors over all the fields. And you know what is especially miraculous, this incredible thing about this, is that X is a finite type over K, over the original, over, I mean, what, I didn't say over the base field, I guess I should say, I didn't say what the base field is. So that tells you all sorts of amazing things, bounds on indices for torsors, bounds on the transcendence degree of fields of definition for torsors, you know, stuff about the essential dimension and so on and so on and so on. It's all captured by this one sort of incredibly simple and beautiful construction. As far as I can tell, I don't fully understand the history of this. I think this was defined in part by Serre, but I know that like Reichstein did a lot of work on stuff like this. Merturiev thought about this. I have not been able to figure out who actually defined this notion exactly. The name for this is a versal.
No, but Grothendieck was the first.
He was?
Yes, yes.
Oh, thank you so much.
This is 1958 paper.
Ah, oh, great. Oh, thank you. Thank you.
You know, when he computed, you know, the torsion index, you know? The Chevalier seminar, yes, 1958.
And presumably he didn't call it a versal torsor. He called it something else.
No, he called it, I don't know, generic, whatever. But this is exactly this torsor he did consider. The more general.
Thank you. Thank you. Thank you. I really appreciate that. Okay, great idea. Beautiful idea, right? Amazing idea. Okay, so, you know, here's the obvious question that you come up with when you see this. What about versal other things? Like, are there versal gerbes? Versal chromology classes of higher degree. Thinking about, you know, torsors as an H1 phenomenon, we can ask about H2, about H3, about H4. And really the target, the idea would be what's important, the key that one wants is some kind of universal space of finite type, or really locally of finite type. Okay. Now there's one clear problem with trying to do this in general. There's an issue. And that is that the indices, index of a chromology class, can be, you know, unbounded. So let me be more precise. If you take, say, G to be, say, like mu n, and we think about H2 of spec of K mu n, as K varies, the index of these classes, index is unbounded. Now, there's a contrast here. If I do this for H1, the index always divides n, because n is the literal size of the group scheme. So any torsor is size n. So the index is always kind of bounded. But for a cohomology of higher degree, there's this problem that something can run away. And so you can't hope to just get a single finite type parameterizing object for this. But you could hope to get something locally a finite type, which would at least carry some transcendence degree information or some kind of interesting information there. All right. Right, now I should say if G is not finite, then I find it still rather mysterious. There's no reason for the index to be bounded. So there's something rather mysterious about linear algebraic groups that are infinite, that are, you know, positive dimensional. There's still something interesting going on there. But for this naive point of view, you can see why H2 is different from H1. Now, if you allow yourself to fix the index also, then there's kind of straightforward answer to what to do to make versal cohomology classes that, as far as I know, was first written down by Krashen. And that goes like this: if you fix G and an index, and let's say G is, I don't know, let's say G is finite. I don't know if this matters, really. Shouldn't really matter. But fix an index, then you can make versal cohomology classes like this. By using spaces of Galois cocycles. The point being that if I bound the index, then there's only finitely many Galois groups that could possibly appear. And over a field, I can compute cohomology using cocycles, and those I can write down as a space. So I can make a kind of finite type, in this case, variety, parameterizing all the cocycles. So I'm going to get the sort of universal cohomology class that way, a versal cohomology class. Does that make sense? I think that makes sense. His paper is more complex than what I just said. He's trying to answer a bunch of other questions, and the way it's written is slightly more opaque than what I just said to you, but that's because he's trying to do something more general. But these things are called presentable functors. But the idea is just if you can write down the universal cocycle, you've written down a versal cohomology class. So abstractly, the answer is not terribly complex. But the interesting part of this is how to make this happen organically. Where can you actually find these things in nature? And I'd say for the versal torsor, there's something very organic about its appearance, even though it's not, so to speak, a moduli problem. For these versal cohomology classes, there's an abstract answer, but it would be nice to understand sort of the organic appearance of these things in this context of sort of Murphy's law, gerbes of definition, and so on. So I want to show you now just a bunch of ways to make gerbes in moduli spaces. So I'm going to just do a few examples and sort of lead into the underlying idea that went into the main result that I stated at the beginning. So how to find these in nature. And the connection with these versal cohomology classes is if you find some moduli space that you understand that has all these gerbes in it, then you've made a natural versal gerbe by restricting to the locus of the moduli space with a given automorphism group. That's the kind of underlying idea. But I just thought I could show you a little bit of a sort of zoo, a tour of some of these methods that we kind of came up with. Some of them are ad hoc, so I want to start with those. So let's think about GM. GM is not a finite group, but I want to tell you here's a way to make any GM gerbe appear in a moduli space, in a natural moduli space. All right, a single natural moduli space. So let G to spec of K. So here's what's going to happen. Any gerbe appears in the stack of stable sheaves on P2. Okay. So I don't know, is this obvious to you? Maybe it's one way to make a GM gerbe appear is you think about you can make it the obstruction to the O of 1 on a Brouwer-Severi variety. So you can always make, if you take the Picard groups of Brouwer-Severi varieties in general, you're going to find all the GM gerbes because that's basically what they are. But my point here is you can actually make it appear in the stack of stable sheaves on just this fixed P2.
No, okay? So sorry, what are stable sheaves?
Oh, there's sheaves that you can also think of as just simple sheaves. Sheaves with endomorphism ring K. Let's think about it. Like the stable part doesn't matter. That's just a technical thing. The important part here is sheaves with small automorphism group. That's something you can.
No, okay. No, okay. No, I mean, this has nothing to do. I mean, this is the usual language for sheaves. I mean,
yeah, right, exactly.
Okay.
Yeah, that's the point, right? It's just like usual sheaves, exactly. Not sheaves on a stack with a this and a that and a blah blah blah. It's just sheaves, right? That's what's interesting about this. But of course, you go through this other mechanism. If I take a GM gerbe of index R, say. Okay, now there's like a trick. Let me just tell you the trick, and it might be a little perplexing, but I'm just going to say it. Okay, so let lambda this terminology might not make sense, but if it doesn't make sense, just ignore this. We'll do another example in a second. Be -1 twisted invertible sheaf on G cross G. So there you can, G sort of splits itself. So there's a special kind of invertible sheaf on it. And then let F be a stable or simple, depending on how what you enjoy, twisted sheaf on P2 cross G of rank R. Okay, and of course, you have to understand why such a thing would exist. It's not trivial. And now here's the trick. Consider G cross P2 and do the following thing. You take per 1, 3 lower star of per 1, 2 upper star of lambda inverse tensored per 2, 3 upper star of F. And what is this? This is a sheaf on G cross P2. And maybe there's a sign error hiding what I did. Maybe this is minus the, oh no, the inversion takes care of that, right? And what this does, this is a family of sheaves on this gerbe cross P2. So this gives an immersion, it turns out, from G into sheaves, simple or stable, depending on what you've set up, on P2 itself. All right. So kind of by this universal line bundle trick, you can stick any GM gerbe into the stack of sheaves on P2. But the thing is that the rank R corresponds to the index of the gerbe. So there's you do replace the hierarchy of all Brauer-Sevier varieties by just the hierarchy of indices. And then you get this sort of model for all GM gerbes, which is the stackable sheaves on P2, simple sheaves or stable sheaves on P2. All right, so that's one silly trick. Let me tell you 2 more tricks, okay? So the second one is, let's say now G is mu n, right? And so G to spec of K is a mu n gerbe. And now I am going to choose a Brauer-Sevier variety, but you'll see this is the analog of what happened with the genus 2 curves. Choose a Brauer-Sevier variety X representing G. And what does this mean? That the Brauer obstruction to O of 1 is more or less G. And now we can choose, okay, I think I'm saying this right, a delta in X, so that O of delta is, so to speak, O of n, even though O of n is not defined. And now again, we consider this gerbe of Z mod n covers, maybe it should be mu n. Let's say mu n covers y to x branched along delta. And now, as I told you before, this is only possible when this is only has a point over L when delta L is in n times pic of XL. And so you see that is exactly telling us that we're getting the right cohomology class. Okay, we're getting the correct gerbe out. And now the thing is that these y's, more or less, if you're careful, if you choose delta to be general enough, it is the moduli of these y's in this stack of all varieties is giving us the gerbe that we're talking about. So the residual gerbe of these so this is realizing this gerbe in the stack of varieties. So this realizes.
Sorry, Max. So sorry, just one quick question. So you're basically saying that you can choose delta so that the automorphism group of X delta is trivial.
Exactly.
Okay.
Yeah. So the automorphism group of Y is just Z mod n.
Right. Yeah. Okay. Okay. Yeah, good.
Exactly. Yeah. Right. Precisely. And so then that sticks that gerbe right into the stack of varieties at that so to speak, at that residual gerbe, the residual gerbe at Y, which doesn't really exist yet. Good. Yes. Perfect. Okay. And now this leads us into sort of what happens in general. If you think about sort of what if we just wanted to realize BG itself? Well, this is an idea, I think this goes back to Serre. If you choose a representation on some vector space that's sort of that you mess with to make stabilizer, the locus with a stabilizer very small in some concrete sense, right? So small stabilizers. Then if you look at, say, general complete intersection, a general, G invariant complete intersection in the projectivization of V has a free G action. You obviously have to be much more careful than what I'm saying to you right now. And this is at least if the dimension is greater than or equal to 2. And maybe you need to say very general if the dimension is 2. There's also things to be careful with here. But the point is, you can make the action be free if you take a representation that's a high enough tensor power and so on and so on and so on, or big, huge construction, linear algebraic construction. Just start taking invariant hyperplanes, intersecting them, invariant divisors and intersecting them. You get something with a free G action. And for large enough dimension, the automorphisms also in general are going to be G itself. And so this equivariant geometry gives you these copies of BG that are sitting in sort of the stack of varieties. Right? I mean, surely, like you've seen, like if you take a general complete intersection, the automorphism group is trivial. So if you do this carefully with G equivariant things, the automorphism group is G, right? And now if you're doing, for curves, there's also some sort of technical, if you take a certain sort of cover very carefully of a complete intersection. Once you have a free G action, you can then do a sort of careful cover to kills extra automorphisms, right? And then again, you get the same thing. You get BG sitting inside of the stack of curves. And so the last conceptual thing you have to realize is that these constructions where you take a representation of G and you think about intersecting G invariant hyperplanes or divisors, what you're really doing, this brings us back to the first thing we were talking about, is in general, so now we've got this gerbe with finite inertia. We can mimic sort of the Serre constructions, but now we work in a vector bundle on G. And so instead of doing these equivariant calculations over K and thinking about automorphisms and whatever, we're just working over G itself, and we're doing complete intersections in a vector bundle or a projective bundle on G itself. So we end up with a family of varieties on G itself where the inertia is acting as the automorphism group. And so that automatically embeds the gerbe into M. That's the idea. That's the ultimate, so I've shown you a bunch of different constructions, ways to try to realize gerbes inside of moduli spaces. The last thing I think that's the interesting part is you can take a lot of these old equivariant constructions over a finite group and realize that you're really just talking about the relative geometry of something over a gerbe. And when you do that, you end up just sticking that gerbe into the stack of curves or varieties or whatever. And that concludes what I wanted to explain to you today. Thank you very much.
Thank you. Is there any question? Any question? Any question? Comment?
Okay, so I have one. I mean, it seems that the year 1958 is quite present in your work. So, first by Grothendieck and secondly by Serre, because I think you refer to this paper, which is called the Mexico paper.
Yeah.
Yes, but in this Mexico paper, what I remember is that the group G is finite and eta. I mean.
Yes, I'm assuming that too. Yes, I'm assuming G is finite.
Okay. So G is finite constant is in what you said.
Yeah, for these for number 3.
Not, because before G was an arbitrary algebraic group, and it is I mean, this is not as simple.
Oh, no, right, absolutely. Right, if you want to have something inside of MG, all the stabilizers are finite. So I was, at that point, I was just thinking about finite gerbes, and gerbes with finite inertia.
Okay,
And-
okay, good. Just okay. So I'm
Yeah, yeah.
I'm fine with that. Thank
And
you.
so, right, so the conceptual, the only kind of change, the only thing you have to realize is, like you said, you could take a constant group and do equivariant geometry. Those constructions still work if you take a gerbe with finite inertia and do relative geometry. Now it's not a constant group anymore, but all the constructions work the same way because they're so universal.
Okay, thank you.
Any more questions?
So there are no difficulties with non-tameness if in characteristic P when the automorphic group is the order of the automorphic group is divisible by P.
I don't think we've encountered those difficulties, but that doesn't mean we won't yet. I have not perceived those difficulties yet.
Okay.
That's a good question. I'll get with Dan and make sure we tease that out carefully.